Good morning. This is the video for AP Stats section 9.1, where we are introducing the concept of hypothesis testing. And on the screen here, hypothesis testing is sometimes called significance tests or just testing a claim. So any kind of all three of those kind of mean the same thing. So we just finished confidence intervals where we didn't know either a proportion or a mean. So we created an interval based on our sample mean. So that was a confidence interval. This is related but a little different. So in this case, it says someone makes a claim or a hypothesis about either the population proportion P or the population mean mu. So those two parameters, P or mu, are still the two parameters we're going to be dealing with. Just like back in chapter 8, those were the two parameters that we made a confidence interval for. So we don't know P, we don't know mu, but somebody claims something about either a proportion or a mean. And then we wonder if there's evidence to support some alternative hypothesis. So you have to look for kind of the original claim and then look for what the alternative hypothesis might be. So we'll kind of throw an example out here and kind of walk our way through this process. Example, I claim that I make 80% of my free throws. Matt thinks I might be a worse shooter than that. So we're always going to have two hypotheses. The original claim is, in fact, I kid you not, called the null hypothesis without the K. Null hypothesis. Null meaning like no change or like the original. And the abbreviation is H sub O. And yes, we're going to call that the HO, as awkward as that might sound. So the null hypothesis is the HO, and then the alternative hypothesis, we're going to abbreviate with H sub A. I'm going to call that the HA. So we have the HO and the HA. The null hypothesis is H sub 0, and the alternative hypothesis is H sub A. So the first thing you'll be asked to do is just to list two hypotheses. So here's my null hypothesis, that P equals 0.8. That's my original claim. I claim that I make 80% of my free throws. This example happens to be about a proportion. It could similarly be about a mean. And then the alternative, it says Matt thinks I might be a worse shooter than that. So that means he thinks my proportion of made free throws is less than 0.8. So that's the alternative hypothesis. And then underneath my picture here, it says this is considered a one-tailed test because you're just based on what Matt says that I might be a worse shooter than that. You're looking for evidence that P is less than 0.8. Let me also show you, let me restate the problem and change one small thing about the wording. What if it said this? Starts the same. I claim that I make 80% of my free throws. Matt thinks I might be lying. It doesn't say that Matt thinks I'm better or worse. It just says he thinks I might be wrong. Notice the null hypothesis did not change. It is still that P equals 0.8. But in this case, we're just looking for evidence that 0.8 is not correct in either direction. So here the alternative hypothesis would be P does not equal 0.8. And that's called, get my picture in the way again, that's called a two-tailed test. Because you're looking for evidence in either direction that the proportion or mean is wrong, as opposed to looking for evidence that it's either less than or greater. So you have to read the wording of the problem carefully to make sure whether this symbol should be not equals to or less than or greater than, depending on the context of the problem. All right, a couple warnings about these hypotheses. The equal sign has to be part of the null hypothesis. It doesn't make any sense to say the null hypothesis is that P is greater than something. The null hypothesis must have the equals. And then this is another common mistake. It says both hypotheses, the null and alternative, must be either about P or mu. You're never making a hypothesis about a sample proportion P hat or a sample mean X bar. Now, we'll be taking a sample proportion and using that to conclude something. We'll get to that. But the hypotheses themselves must be about the population parameter, either the population proportion P or the population mean mu. Okay. All right. So now we're going to test this claim. That's why it's called hypothesis testing. So Matt, I claim I make 80%. Matt thinks let's go with the less than. Matt thinks I'm worse than that. So let's say I shoot 100 free throws, which leads to a sample proportion p hat. Let's say this particular time I shoot 100 free throws and I make 76 out of 100. That means my sample proportion happens to be 0.76. Remember that that's just one sample proportion. And it says here in this law that that one sample proportion is part of the sampling distribution. Remember, we talked about those in chapter 7. If I were to take 100 free throws and calculate a sample proportion, and if I were to do that again and again and again and again and again, I would create a sampling distribution of sample proportions. So my one sample proportion, which happens to be p hat equals 0.76, is just one number of that sampling distribution. Now, this sentence is important. It says clearly we don't expect me to make exactly 80%, even if P really is 80%. If it is true that I'm an 80% free throw shooter, if I just took one set of 100, you would not necessarily expect me to make exactly 80. There's going to be normal variability. I might make 76% one time, I might make 85% one time, I might make 81% one time. Now, would you expect me to make all 100? Maybe not. Would you expect me to make like 3 out of 100? Maybe not. But certainly there would be some variability. So you cannot just look at the sample proportion, which is 0.76, and you can't conclude, oh, since that's less than 0.8, Matt must be right. He must not be an 80% free throw shooter. That's not how it works, because again, you're going to expect some, due to the randomness, some variability in the values of p hat. So the question is not just simply, is p hat less than 80? The question is this, and I put it in all caps because I guess I'm feeling like yelling at you all. It says, how likely, and that's a probability, how likely is it to get a result as extreme or more extreme than the result we got if the null hypothesis is true? Let's figure, I need to have you digest that. If the null hypothesis is true, which in this case is, let's say I really am an 80% free throw shooter, how likely am I to get a result like 0.76? Anything that low or lower? What's the probability of doing that poorly or worse? That's the probability we're going to calculate, and we're going to want to know. And then this probability, again, my picture's in the way once again, this probability is called the p-value. When you're calculating the p-value, that is, how likely is it to get a result as extreme or more extreme than the one that we got? So let me show this to you visually. Here is a picture, and I have this. Remember, if the right conditions are met, and we'll get to the conditions in the next section, it would be a approximately normal distribution, and 80% is the middle. And if 0.8 really is the true proportion, my result was 0.76. The question is, what's the probability of getting a result as extreme or more extreme than the one that I got? So that is this shader. So the question is, what the p-value would be, that probability. And this line just kind of states as an expression, the p-value is the probability that p hat is less than 0.76, given the fact that the null hypothesis is true, which is that p equals 0.8. Now, in this first section, we're not calculating the p-value. The problem's going to tell us what the p-value equals. In the next section, we'll see how to use the calculators to calculate it. So I did the math, which we don't need right now. It turns out that the p-value in this case is 0.1596. About 16%. What does that mean? That means if I really am an 80% free throw shooter, if I shoot 100 of them, I've got a 16% chance, just based on random variability, 16% of the time, I'm going to make 76% or fewer. And I would argue that 16% is not particularly rare. That's just, it's going to happen sometimes. Again, would I ever make 3 out of 100 if I really was an 80% free throw shooter? Probably not. That probability would be much smaller. But it turns out that p hat value of 0.76, a value that extreme or more extreme, happens 16% of the time. That's not particularly rare. Well, but now let's look at another sample proportion, same problem. Now it says, what if p hat equaled 0.6? What if again, same scenario. I claim that I make 80%. Matt thinks it's less. So I take 100 free throws. I only make 60 out of 100. That is 0.6. Well, again, we're not worried at the moment about calculating p. It turns out in this case, look at that p-value. What does that mean? If you're asked to interpret the p-value, that means if p really equals 0.8, if I really do make 80% of my free throws, then the probability of me making 60% or fewer is 0.000003. That is extremely unlikely. So that is so unlikely to happen by random chance. That's evidence that maybe Matt was right. Maybe the null hypothesis, which is that p equals 0.8, is not true. So that would be evidence, that very strong evidence that the null hypothesis must be false, which is the same thing as saying that's evidence in favor of the alternative hypothesis, which is that p is less than 0.8. But we're not proving anything. Maybe I can do it. The probability here is really, really, really small. But for the other one where it was 16%, just because I happen to make a fairly rare percentage, doesn't prove that the p is less than 0.8. We're just looking for strong evidence. We never want to use the word prove anywhere in these things. We're never proving anything. So, all right. So now this phrase, again, I apologize for. It says if the p-value is low, we reject the hoe. So you are allowed to memorize the phrase: if p is low, reject the hoe. That's how it works. And if we reject a hoe, that means there's evidence to support the ha, evidence to support the alternative hypothesis. And then look at this next one, because this is also, excuse me, the wording is important. It says if the p-value is not low, we fail to reject the hoe. We're not accepting, we haven't proven it's true. There just isn't quite enough evidence to reject it. So if I made 76% in my one sample, and the p-value is 16%, that's not that low. So we failed to reject the null hypothesis. We haven't proven that 80% is true. There's just not enough evidence to reject it. So the conclusion you're going to make in one of these significance tests or hypothesis tests is either to reject the hoe, reject the null hypothesis, or fail to reject the null hypothesis. That's important warning. So you're always going to conclude either reject the hoe or fail to reject the hoe. So now the question is, and I just kind of breeze through this, how low? Like, how low would that probability need to be in order for me to decide, okay, that's rare enough by random chance that I'm going to reject the null hypothesis. So that whatever that percentage is called a significance level. And we're going to use the Greek letter alpha for that. And even kind of like with confidence levels or confidence intervals, either the problem will tell you what level to use for alpha. Otherwise, we're going to default to 5%. That's kind of the agreed upon. If it's going to happen, if the probability of it happening is 5% or less than 5%, that's rare enough for us to say that's evidence to support the alternative hypothesis. Is it proving anything? No. We might have just gotten a fairly rare, but not that rare, 3%, 4%. So it doesn't mean it's possible we're making the wrong decision, and we'll get to that. But if p is less than alpha, which in this case is 0.05, we will then reject the null hypothesis. Okay, so the next thing I want to talk about is, or the last thing in this section is, what if in fact you make the wrong decision? So we already said if, let's say in this case, my p hat was 76.76. I took a sample, I took 100 free throws, I made 76 of them. And that p-value was only 16%, which is not that rare. So we failed to reject the hoe. There was not evidence to support Matt's hypothesis that I'm worse than 80%. But I might be worse than 80% free throw. So if I fail to reject the null hypothesis, but I actually should have, that's one type of error I could make. And there's also the other type. What if my result is rare enough that I do reject the null hypothesis, but it turns out that I really am an 80% free throw shooter. I just happened to have an unusually bad sample. So I reject the null hypothesis, there's evidence to support Matt's hypothesis that I'm worse than that, but it turns out I really do make 80%. That's another error I could make. Well, in statistics, those are called type 1 and type 2 errors, and you need to know which one is which. And this table will help us with that. So it says, what if you happen to make the wrong decision? So the truth is either that the hoe is true or false. Like either I am an 80% free throw shooter or I'm not. We might not know whether it's true or false. One of those has to be the case. And then the decision that I make based on my hypothesis test is either to reject the hoe or fail to reject the hoe. So I have four possibilities. Either it's true and I reject it, it's true and I fail to reject it, it's false and I reject it, or it's false and I fail to reject it. Well, of those four options, two of them I've made the right decision. I've already labeled those two boxes here. It says correct decision. So in this box, if it turns out that I'm not an 80%, that I'm worse than 80%, and my test leads us to reject an hypothesis, we made the right decision. Good for us. And then down here, lower left, if it turns out that I really am an 80% free throw shooter, and the test we do fails to reject it, again, we made the right decision. But the other two empty boxes there, other two possibilities, are where I'm making the wrong decision. Top left, if the null hypothesis is true, but I reject it. So if I really am an 80% free throw shooter, but my test leads me to reject the null hypothesis, that is a type 1 error. And then the other one, if it turns out that I should have rejected it, turns out I'm worse than 80% free throw shooter, but the test tells me to fail to reject it, that's a type 2 error. And then the sentence that I have stuck in my head that helps you remember this, don't get it backwards, is this. The first one in particular. If you reject a true null hypothesis, that is a type 1 error. So if you can remember that sentence, you can figure out the other possibility, which is failing to reject a false one. But if you reject a true null hypothesis, that's a type 1 error. And then the other thing you might be asked to calculate is, what's the probability of making one of these types of errors? Well, it turns out that to find the probability of a type 2 error is statistically beyond the scope of what we're working on. But a type 1 error, let's figure out what that is. Type 1 error, that I reject a true hypothesis. So if I really am an 80% free throw shooter, what's the probability that I incorrectly reject it? Well, any p-value less than 5%, like if I happen to get a result that only happens 5% or less of the time, I'm going to reject the null hypothesis when I should. So it turns out, this is good news actually, it turns out that the probability of a type 1 error is in fact alpha. Whatever the significance level is, that's in fact kind of what we're defining alpha to be. It's how rare does something have to be in order for me to reject the null hypothesis? Well, let's say we're using 5%. That means that 5% of the time, I'm going to, even though the null hypothesis is true, I'm going to get this rare but not unheard of result. So you need to know that the probability of a type 1 error is in fact alpha. Okay, so there's the explanation of 9.1. Here's your homework assignment. And then, like I said, we'll probably be in a video on Thursday/Friday, kind of starting 9.2. And as maybe I didn't tell you, I only said this in class. Just like the last chapter, 9.1 just kind of introduces the concept of hypothesis test. And then 9.2 is a little more specific about testing a proportion. And 9.3 is a little more specific about testing a means. That's kind of where we're going with the rest of chapter 9. But it will not take us long to get through chapter 9 at all. So have a great day.